Okay, let's look at some extended u-substitution techniques, and this lesson assumes you already know the basics of u-substitution and finishing an indefinite integral. In this lesson, we're going to look at something that I call double substitution. We're going to look at some definite integrals and integrating with rational expressions or rational functions. If you want to print this sheet to follow along at home, you can go to this bit.ly link right here. That is what I provide for my students. And so let's talk about u-substitution. And one main thing to remember with u-substitution is when you are actually doing the substitution, when you're removing variables of x and replacing them with things of u, that act of substitution is an act of algebra. And as long as you're camping out in the world of algebra, you are allowed to manipulate your equations, whether it's your u equals expression or if it's your du equals expression. You're allowed to manipulate those in any algebraic way you want to allow you to substitute every x out of the original equation. And so the first one I'm going to talk about is something called double substitution. I thought I made this phrase up myself, but then I saw it on AP Central's website, so maybe I'm not as clever as I thought. But this is a method that you can use when you're able to satisfy your du. And I tell my students that the most important part of substitution is to account for that du. But sometimes when you substitute your du in and you do everything you can easily do, there are still some x expressions left over that need to be dealt with. And so that's what we have right here with example number 1. And this one I'm going to use substitution, and I would let u equal the interior x minus 4. If that's your u, the derivative of x minus 4 is 1 dx. And I see my du in the problem already, so I can go ahead with u substitution, and I would start by replacing that dx with a du. So the dx comes out, I'm going to put a du in its place, and for a hot second, we still have an x and an x minus 4 to the 8th remaining to deal with. Now the x minus 4 is going to be easy, because x minus 4 is equal to u. So I can take out the x minus 4 and I can put a u in its place. And so instead of x minus 4 to the 8th, I now have u to the 8th. But then I'm looking at what's left and I still have this extra x left over. And here is where double substitution comes into play. So I'm looking back at my u expression here. I'll just erase that. U is equal to x minus 4. And if u is equal to x minus 4, here is where I'm going to do some algebraic manipulation here. I can go really crazy and I can add 4 to both sides of that equation. And I can say that u plus 4 is equal to x. Well, if u plus 4 and x are equal to each other, then I can take this x out and I can replace that x with a u plus 4. And with that, I have successfully substituted every x out of the original problem and replaced them with their u equivalents. And the idea is that the new antiderivative is something that is easier to actually integrate. And so what we have now is u to the 8th times u plus 4. And for this one, it's currently a product, but I can very easily expand that. I can distribute that u to the 8th quite easily. U to the 8th times u is u to the 9th. And u to the 8th times 4 is 4u to the 8th. And with that, I now have a nice clean power rule, which is the object of u substitution. It's to take something that's ugly and turn it into something that's a little bit more manageable. And I've done that. Now, if you want to look back at the original problem, I suppose we had the option of expanding, but expanding x minus 4 to the 8th is going to take like 10 minutes if you don't make any mistakes, and you're going to have this incredibly long polynomial that's really complicated. So we're definitely going to go dub sub on this one. And now that I have a power rule, we can very quickly crank out this antiderivative. The antiderivative of u to the 9th is u to the 10th over 10, plus the antiderivative of u to the 8th is u to the 9th over 9. The 4, that was the coefficient of u, just comes along for the ride. And then we need to remember to plug our u back in. U was equal to x minus 4, so my final answer is x minus 4 to the 10th over 10, plus 4 times x minus 4 to the 9th over 9, and don't forget your constant. So there's one example of double substitution. I'm going to look at one more. And on this one, we have x root 2x minus 8 dx. Again, I'm going to go u sub here. The u is going to be the 2x minus 8. du is 2 dx. And the way I like to do u substitution is I look at what my du is. The derivative of 2x minus 8 is 2. And I want to see that in the original problem. I have the dx, I'm missing the 2, so what I like to do is squeeze a 2 in here. So I'll multiply the dx by 2. However, if I multiply by 2, I need to offset by dividing by 2. I'll put a 1/2 out here. And so this now turns into 1/2 antiderivative. The 2dx is my du. And then I start looking at everything else that needs to be substituted. And for the radical expression, 2x minus 8, that's going to be pretty easy to substitute 2x minus 8 out, replace that with a u, but I do again have this x remaining that I need to account for. It has not been substituted out yet. So I take this expression, and if u is equal to 2x minus 8, then x is going to equal u plus 8 all over 2, and then I can replace the x with that expression. So now I have u plus 8 all over 2. And again, we're looking at this trying to figure out what is going to be the convenient way to do this antiderivative. All my x's are out, all my u's are in, so we're reevaluating this new problem. And one thing that I see is this division of 2 right here, that's a 1/2 right here. I can actually take that 1/2 out of this integral. I don't really like that 1/2, and I'm going to move it in front of my integral. I'm going to take that 1/2 out, and I'm going to rewrite this expression as 1/4 of the antiderivative of u plus 8, and the square root of u is the same thing as u to the 1/2 power. And now we have a situation that's almost identical to the one we just had. This is a little bit uglier because we have the fraction exponent, the rational exponent there, but I have an expression where I can distribute through the binomial, just like we had in number 1. The distribution here, you just have to be a little bit more careful, because when you distribute, remember you add exponents, and so I will have, the 1/4 outside just stays there. I'll have the antiderivative, u times u to the 1/2, you add the exponents, you get u to the 3/2, plus 8u to the 1/2, and we once again have a power rule. It's a fraction-y power rule, but it's still a power rule, and I'm going to find the antiderivative of that. And at the same time, as I find the antiderivative, I will also replace my u's with the 2x minus 8 that I originally set them equal to. So the antiderivative of u to the 3/2, 3/2 plus 1 is 5/2. And when you divide by 5/2, you multiply by 2/5. And I'm just going to go ahead and replace the u with 2x minus 8 plus 8 times, I'm going to do 8 times u, 1/2 plus 1 is 3/2. We're going to divide by 3/2, which is times 2/3, and the u is 2x minus 8, and all of that plus c. And you can clean up this little thing right here. 8 times 2/3 is 16/3 if you want to make it a little bit more aesthetically pleasing, but that's an algebraic maneuver, and I want to show you the calculus. So there's number 2 on double substitution. And let's look at another type of problem. And this is dealing with definite integrals as it relates to u-substitution. And another thing to remember is when you are doing u-substitution, once you start converting things that are in terms of x to their equivalents of u, everything that was related to the old variable, and I'm using old variable kind of liberally there, the original independent variable, which is typically x, it needs to be converted to its equivalent of u. And so as you do your substitution, make sure that everything is turned into their equivalent value of u, which is what we did with the double substitution. We make sure that every one of the x's was converted. Now when there's a definite integral, the limits of integration, the original limits of integration, are also values of x. And since those are values of x, you can also convert the limits of integration. Now, I put the little word can very small there because this is not an absolute necessity in certain situations. But I personally prefer to always convert the limits of integration. And I'll show you what that means. So I'm going to first show you how I would solve this without converting the limits of integration. I'm going to go a little bit quickly because this is a fairly clean u substitution. I'll let u equal x squared minus 1. du is 2x dx. I have the 2x dx ready to go, so that's going to be replaced with my du. The x squared minus 1 is my u, and so my new antiderivative is going to be just u to the 4th du. And the antiderivative of u to the 4th is u to the 5th. Then I would plug the x squared minus 1 back in. X squared minus 1 to the 5th over 5. Then I remember this is a definite integral, so I need to evaluate this from 1 to 2. So we don't worry about those limits of integration until after we have found the antiderivative. Now if I plug in 2, 2 squared is 4, 4 minus 1 is 3. That will be 3 to the 5th over 5. Plug in 1. 1 squared minus 1 is 0. And so your answer is 3 to the 5th over 5. Now, if you want to solve your definite integrals and u-substitution this way, that's perfectly fine. It works in the end. Just remember that 1 and 2 are values of x and must be plugged in for values of x. What you do not want to do is when you write your u-substitution in terms of u, is to write 1 and 2 right here, because you might be tempted when you find the antiderivative to plug in 1 and 2 for u, which ends up giving you a different answer. If I plugged in there, I would get 2 to the 5th over 5 minus 1 to the 5th over 5, which is not the same as the right answer. So be very, very careful with those limits of integration. The original limits of integration of 1 and 2, in this case, must be plugged in for the x. However, there is another way to do this. I'm going to show you that on the next page. And what I'll do here is I will just copy this initial work that I have right here up until the point I substitute the x squared minus 1 back in, because the other way you solve this, you're going to go through all of these same initial steps. You're going to pick a u, you're going to identify the du, you're going to substitute it, you're going to find the antiderivative. However, you have the option of also converting the limits of integration. Yeah, integration. Converting, I'll say convert limits of integration. Okay. The original limits, which are still up here, are in terms of x. That's x equals 1 and x equals 2. So if x is equal to 1 and u is equal to x squared minus 1, then u is going to equal 1 squared minus 1, which is 0. And so since I've converted that lower limit of 1 to its equivalent of u, I can put a 0 here. And if x is equal to 2, then u is equal to 2 squared minus 1, x squared minus 1, which is 3. So when x was 2, that converted to a u limit of integration of 3. Now I can finish the problem and never go back to x's. I don't have to plug my x squared back 1 back in, because now that I've converted my limits of integration to u values, I can evaluate u to the 5th over 5 from 0 to 3, which would be 3 to the 5th over 5. Minus 0 to the 5th over 5, and you'll see we got the exact same thing we got the first time, and really the amount of work is the same. This is really not a more efficient method. I think it guards you against potential mistakes better. Either way you solve this, you will have to plug in 1 and 2 to the expression x squared minus 1. The question is, when do you want to do it? I prefer to do it at the very beginning and get it out of the way so I don't accidentally plug 1 and 2 in for my u values. You do have the option of waiting to plug 1 and 2 in at the end, but again, you have that potential mistake where you may accidentally plug them in for the wrong value. So I personally prefer to go ahead and convert my limits right at the beginning so that I can just go ahead and finish in terms of u and never have to worry about x's again. And then one last thing I want to talk about this is antiderivatives as it relates to rational expressions. And a reminder for you from Algebra 2 and Pre-Cal, a rational expression is any fraction where your numerator and denominator are both polynomials, and polynomial means strictly x to an integer power, and really a whole number power. It has to be a positive integer power. And when you are when you're doing antiderivatives of rational expressions, you really want the degree of the denominator to be greater than the degree of the numerator. So your bottom degree needs to be bigger than the top degree. If it's not, if your top degree is equal to, or if your top degree is less than the bottom degree, we have to fix this. And the way we fix that is we will divide the bottom into the top. So anytime you are doing antiderivatives and you notice that your bottom degree is not bigger than the top degree, we are going to fix that right off the bat before we do anything else. And the way we do that, well, I've already said we're going to divide in. So the most obvious one, I think, is long division. And long division, I believe, is the safest route. There is a faster route if you're dividing by a linear divisor. Yes. You can use synthetic division. It's very fast. However, it's very easy to mess up. Long division, I believe, is the safer route. And then on rare occasion, and I'm not going to do any examples like this, you might be able to factor the numerator and cancel the denominator with the numerator. And if that works, that is also fairly fast, but it's not something that happens very often. So I have one example of this that I want to look at. We have this rational expression, x squared minus 2 over x plus 1. They're both polynomials. However, my top degree is bigger than the bottom, and I don't like that. Now, just to be completely transparent, it is possible to let u equal x plus 1, du to equal dx. I have my du right here. I have u in the denominator. I still have an x squared on top, and so it is possible to dub sub this and let u minus 1 equal x, plug u minus 1 in the numerator, square that, expand it. You'll then have an algebraic expression you can reduce through something I call STDs, but I'm not going to do that this time. I just want to let you know that it is possible to finish this with more traditional u substitution. That said, I want to show you how to do this by dividing. And while synthetic division does indeed work, I firmly believe long division is the safer route. You're more mathematical in solving or dividing with long division. So I'm going to divide x plus 1 into x squared. There are no x's. I prefer to put that placeholder there. And when you're doing long division, you look at this x and I think x times what gives me x squared, and that would be x times x. Then we'd multiply that x through the x plus 1. That gives me x squared plus 1. Then we subtract this whole thing. I need to subtract x squared plus 1 from what's above it, which means x squared minus an x squared, and 0 minus a negative 1. And if you're doing long division, that first one should always subtract out to 0, which it does. 0x minus 1, and that should be minus 1x, not minus 1. So 0x minus 1x is negative x. I'm going to bring down my negative 2, and then we rinse and repeat. X times a negative 1 will give me that negative x. I distribute that negative 1 through, so we have negative 1 times x, negative 1 times 1. And then I will subtract that from what's above, which means I need to change the signs. I'm going to make that plus x plus 1, and negative 2 plus 1 is negative 1. Those zero out. And after doing that division, this final number right here is your remainder. So we have plus a negative 1 over x plus 1. So I've now done division. I've divided my bottom into the top. And what you need to remember is this is an act of algebra. This was not the antiderivative. What I have done now is I have rewritten my original expression like this. And so now I need to find the antiderivative of x minus 1 minus 1 over x plus 1. And I just took that negative 1 on top and made that a minus the fraction. And we have a new antiderivative. And so right now what I can really do is just ignore everything I've already done. I have a new problem. How do we do this antiderivative? Well, the antiderivative of x is x squared over 2. The antiderivative of 1 is x. And this fraction, I notice my numerator is the derivative of the denominator. That one was ugly. And if the numerator is the derivative of the denominator, that means the antiderivative is the natural log of the denominator plus c, and there is your answer for number 5. And so there's your approach if you have a rational expression where your bottom degree is not greater than the top degree. Do division, and then you do the antiderivative of that new quotient when you divide the bottom into the top. And that is it for this lesson, I believe, and it is.